Hi everyone, I'm Yunmo Zhang from City University of Hong Kong. And today I'm glad to present our work about inferring a class of atomicity program property for persistent memory. And this is joint work with my advisors Junqiao, Hong, and Jason. So let's start with some basic background. So persistent memory is introduced with the advantages like byte-addressability and avoiding the storage stack overhead. This allows for the directly operating on the persistent data in memory. Well, the challenge is the persistent memory themselves need to ensure the crash consistency. This is because writes are buffered at the volatile area and then flushed to the PM in an arbitrary order. So programmers need to use the low-level instructions like flush and fence or transaction interfaces to ensure the crash consistency. But obviously, it's error-prone. And typically for a sequential PM program, there are three types of requirements for achieving the crash consistency. The first is durability, that stored to PM needs to be persisted with an explicit flush instruction. And the second type of requirement is ordering, that stored to an address in PM needs to be persisted before another one. And there are also requirements for the atomicity, even for a sequential PM program, that a set of PM stores needs to be persisted together, usually with a transaction interface protecting the updates. So since using this low-level instruction, it's very error-prone. In the last few years, there are extensive PM testing tools proposed. Early work mainly focused on detecting the durability bugs, that is the simplest form of the crash consistency violations. The recent work focused more on the application-specific ones, including the violation of ordering and atomicity requirements. So to detect the application-specific violations, aside from the PM programs and traces as the input, these testing tools usually require the crash consistency oracles or the PM property in the literature. And to specify these PM properties, the first method is user annotation that lets the users, for example, to explicitly tell the testing tool which variable should be persisted before another one. It is time-consuming and still error-prone. So there's another line of work that resorts to the persistent model. So the simplest form of persistent model is strict persistency that requires every PM write is ordered with the previous PM writes. And there are also other models that reduce the persistency problem to the memory consistency model, such that the existing tools for checking the memory consistency could be also used for the persistent model checking. Well, the problem for this line of work is that they only support the ordering properties. So PM properties could also be inferred by tools. There are some work in this direction that many focus that based on the dependency analysis, that use dependency analysis. This work could cover part of the atomicity properties. They fail to infer a class of critical atomicity properties that I will discuss and introduce now. So consider a persistent adaptive radix tree. Here, a child pointer is appended to the N4 children node array. So here is there's a variable children count, tracking the number of valid elements in this children node that also needs to be updated. So to ensure the crash consistency, the updates of children array and the children count needs to be persisted atomically, because otherwise, upon a crash, partially persisting any of variables will induce some problems. For example, partially persisting the children count will lead to the return of the dangling pointer and the partially persisting children array leads to the data loss because the children count could not correctly track the number of persistent elements in the PM. So in our work, we focus on this type of atomicity properties, and this involves variables between the container-like arrays and the integer variables that track the numerical values about the logical size of these container-like arrays. And we refer to this kind of correlation between array and integer variables as a counting correlation. So we specifically observed that this counting correlation exists in 3 scenarios. The first is the simplest one, that the integer variable tracks the logical size of an array or the number of valid elements in the array. The integer variable could also represent the sum of the logical sizes of multiple arrays. And the third one is the integer variable represents the complementary size of an array to a constant. So this counting correlation exists in many PM data structures. Aside from the trees I just mentioned, they exist in the data structures such as ring buffers between the continuously allocated buffer and its head or tail of sites. Or it exists in the relationship between the hash table and its capacity variable that used for the future resizing operation. And this correlation also exists in other traditional storage stacks, and there are some violations ever found in the real system. For example, in Btrfs, metadata ISS is ever found to be mismatched with the actual file size after fsync the appended data to the file when some important flags are not set properly. So the existing property inference approach hardly infer the counting-related properties. This is because they are mainly based on the control dependency patterns. They assume that the atomic variables are control dependent by other variables, or the control dependent by each other. In other words, these atomic variables acting as the guardians in the if conditions. However, if we consider the counting correlation, here's a container-like array rarely act such role in the program. They rarely appears in the if conditions to guard other variables. So that's why the dependency analysis approach hardly capture the behaviors of container-like variables and failing to infer such properties. So our idea is to infer the counting-related atomicity properties by directly capturing the semantics. Well, the problem is, although the definition of such correlation is very intuitive, expressing its semantics is not as straightforward. This is because the value of the integer variables is not always equal to the logical size it is intended to represent throughout the program. So in a simple example of inserting an element to an array, the value of the logical size may be not consistent with the real numbers of the array, maybe not consistent with the real numbers of the elements in the array during the process of the ingestion. So in our approach, we aim to answer 2 questions. The first is how to capture the semantics of the counting correlation, and the second is how to infer the counting-related PM properties. For the first question, we observe unpredictable behaviors of the counting-correlated variables related to their access range. And we name these predictable behaviors as kind of access range invariants. And we use predicates to describe them to be checked against the real program behaviors to infer properties. And for second question, we use symbolic range analysis to extract the access range behaviors, and we validate the counting correlation by SMT constraint solving. So for capturing the semantics of the counting correlation, our main observation is that all arrays to the container-like array have their address within an area restricted by the by its logical size variable's value. So this is because the array behaviors themselves actually encode the program's intent for acquiring the valid elements from a container-like array. So in our running example, the read index I has the edge with the upper bound being the logical size variable, although it's not yet updated and may not consistent with the final size. So formally, we use some predicate to describe this read access range invariant. For example, here shows a predicate under scenario 1. It tells that every read index to the array is less than the logical size variable's value. And we could extend this idea to other two scenarios. For example, for scenario 2, we changed the predicate accordingly to incorporate the read indices of n arrays instead of one array. And for scenario 3, we changed the upper change the constraint being the read index is less than the constant minus the logical size variable value. So next we could infer the counting-related properties because we already have the observation of the read access invariants. We propose to use symbolic range analysis to extract the symbolic values of the array access indices. And then we generate the candidate variable pairs or variable groups. And for each candidate variable pair or group, we validate if it satisfies the predicates of the access range invariant we just mentioned through the constraint solving. If the validation succeeds, an atomicity property is generated. So, in inferring the property, at the first step, after applying the symbolic range analysis, we could get the symbolic values of all the integers in the program, including the all the array read indices. And next, we generate the candidate variable pairs by only selecting the integer variables that appear in the symbolic value of array access index. And finally, we validate if this candidate pair or candidate group follows invariants. So this is done by constructing an invariant constraints, which is a conjunction of the constraint that each read index is less than the candidate integer variable value. And our goal here is to check the satisfaction of this invariant across all the possible values of the integer variable. So we use SMT solver to check the negation of the invariant constraint. And if it is satisfiable, meaning that we could find an assignment that violates the invariant, then the invariant is unsatisfied. And if the solver result is unsatisfiable, it means that the invariant holds for all the values. Then a likely PM atomicity property is generated. So in our evaluation, to test the effectiveness of our inference approach, we use the infer PM atomicity property to discover bugs in 4 popular PM data structures. And we compare with the inference approach, other inference approach, including the dependency-based ones that designed specifically for PM, and some traditional ones that designed for the concurrent programs. So the results show that these infer PM properties could detect 14 bugs, with 11 of them are new. And most of the bugs succeed the capability of other inference approach. And due to the static analysis method we used, each analysis, the analysis time for each testing program is less than 1 second. So to summarize, we observe counting-related atomicity requirements for the quadratic consistency of PM programs, and we propose to use some predictable read access range to encode the semantics or the programmer's intent of these variables. And we design an inference approach based on symbolic analysis and constraint solving. Our evaluation validates the effectiveness of our approach and the existence of such counting-related atomicity bugs. Thank you. That's my today's talk, and I'd like to take any questions.